sufficiently cheap that you can do large enough system and large enough bases to have things that are well converged. In practice, it's very hard for many body methods to do this directly. So what I'm proposing, or what we're focusing for the most part, is the idea of composite approaches. And by this, I mean you want to combine methods. You want to use things like low order perturbation theory or even mean field approximations to capture whatever, to develop corrections in such a way that you can mimic the idea of getting to this limit, but staying some in here with your correlated method. This is very standard in quantum chemistry calculation, for example, where you combine MP2 and couple cluster to apply, to get some sense of basis set corrections, for example, in small systems. But in solids, we have to think about system and basis, and the two of them talk to each other to some degree. Then another thing that we have to think about is that the computational cost is quite high and the memory cost is also enormous. We have to store, and I'm sorry to go back because I didn't emphasize that, we have to store this quantity in this language, which scales as the 4th power of the size of your basis, which is quite a harsh problem. So we have to deal with computational efficiency, with code that can handle and can efficiently deal with this complicated object. And at the same time, we have to keep in mind these two limits in mind. Sorry, wrong way. The first thing that we did, this was a couple of years ago, is to really focus on how to re-implement the algorithm with the concept of memory consumption in mind, and with the concept of modern architectures where we don't really have that much memory when we think GPUs, and I'm going to say a little bit more about that. So, of course, this is borrowing a lot of ideas from quantum chemistry as much as we can. The first thing that you do, and this was already done by Sheway and some original AFQMC calculations, is to rely on the Cholesky decomposition, where you don't ever store the 4-index quantity directly. You store some tensor decomposition, in particular some 3rd-order tensor decomposition. Recently, we generalized this idea and rewrote auxiliary field, also using tensor hypercontraction in mind, where now the 4th-order tensor gets written as some combination of essentially matrices. And you can go to this paper if you want the details, but this gives you a very significant reduction in the memory consumption of the system. Also, quite importantly, if you want to do solids that do have periodicity in mind, if you have K points, for example, in the system, you can incorporate directly momentum conservation in your Cholesky decomposition, and this also brings a quite dramatic reduction in memory consumption. So by combining effectively these type of representations, we are able now to do systems that before we did this were thought to be nearly impossible, right? So now we can do, as I will hopefully show you, hundreds of atoms in a fairly routine way, what I'm going to call routine. The other aspect of this is the GPU implementation is quite essential. As you might know, GPUs are notorious number crunchers. So if you have high density compute-bound calculations, which is very what auxiliary field is, and the GPU would be particularly suitable for this type of calculations. And in this figure, I'm showing just an example of sort of the time that it takes to do calculations based on the different representations, which is what I tried to mention before, and in the GPU, and so CPU versus GPU. And you can see that the speed ups that we get with the GPU are enormous. We're talking factors of 30, 40 compared to a CPU only calculation. And that not only allows us to get smaller time per step, but also allows us to reach system sizes that before were essentially impossible. So before I started doing these calculations and before the GPU implementations came into line, doing a 50-atom calculation requires supercomputing time, require allocations in big clusters, thousands, of course. Now we can do several, let's say 100-atom calculations in a handful of nodes with GPUs for a few hours. So the speed up that we get really allows us to think next step in terms of what we can do with the method, and we don't have to worry so much about the computational expense, which, by the way, AFQMC does have a bad reputation for being expensive. So hopefully with this, what I show you is that if you're willing to take the step of working on GPUs, the speed ups that it gives you allow you to really take the next step in applications and to make it competitive with other things. Efficient basis sets are essential. After several years of working and trying to do real materials with this, the one thing we realize is that the basis set error is really the thing that's going to kill you more likely than not. And so hopefully I get to convince you of this. In this figure, this is some recent work that we did as part of a collaboration, as part of a work with the QMC-PAC team. So QMC-PAC, by the way, is a large scale package to do variational diffusion and also auxiliary field quantum Monte Carlo calculations. We did a study we took carbon, lithium, fluoride, and aluminum, and we tried to compare as best as we could the pros and cons of the two methods within a apples to apples comparison as well as we could. So what I'm showing here is the percentage of the correlation energy that we get with both DMC and AFQMC for all three materials for different basis sets. In the case of auxiliary field calculations, of course, the auxiliary field calculation lives in the basis set. So the best you can do is the exact answer within that limit. And that number would be what you get. Sorry, you might not be able to see it, but every time you see a darker and a brighter color, the dark color is the percentage that you get if you do a single determinant trial wave function. The shaded or lighter color, both in green and blue, is what you get if you put multi-determinant in your trial wave function and you push this to convergence. And so for here, for example, this gives you an idea of what the error bar is. The error in the energy as a function of the number of determinants in your trial wave function for both DMC and auxiliary field. There are two things to notice. The first one is that AFQMC converges very quickly and has a very small error already at the single determinant level. But not only that, adding a few hundred determinants is enough to erase this effectively. So if you see at the different curves here, the amount of light blue is very small. And what you get, because we are pushing it to convergence, this is the error that you're making and how much you are removing by adding multi-determinants. The same thing on the green, right? The dark green is the single determinant error. And if you push multi-determinants, this is as far as you get with the type of resources that we put into this. The number of determinants that you need in DMC is usually pretty large. You're gonna need several orders of magnitude more determinants to get the same accuracy than auxiliary field. But the basis set error in DMC, of course, is very small because DMC in principle works in the basis set limit. Even though there is a residual basis set error, this is representability of the trial wave function within that basis. So it's not really basis set error, it's still the fixed node approximation enforced by the basis that we use to represent the trial wave function. In our case, we do the calculation in the finite basis. So what you see here is the exact answer within that basis. As you see, we have a very large residual basis set error because the bases that we're using are finite and are reasonably small, but the answer within that basis is very accurate, and the improvement of whatever residual error we have in auxiliary field is easily recoverable with small determinant expansions. So you sort of pick your poison. If you are willing to fight the basis set error, if you prefer to fight basis set errors, pick auxiliary field. If you want to be closer to the basis set limit, but rather fight the wave function error, then DMC might be better. Honestly, this is, I think both methods are exceptional. They're both methods that are worth looking at. In this particular scenario, this is how it's showing. We don't really know. We haven't done this in more correlated problems, but we'll see. So we understand now that basis sets are essential, that we really need to be able to capture as much of the basis set error as possible with as simple calculations as possible. Keeping in mind the idea of composite approaches, we're not going to propose or rely on extrapolations to the basis set limit every time. What we really want is to find a basis that captures as much as possible of the correlation energy and find a method that will give me the difference as cheaply as possible. And so with that in mind, the first thing that we started doing several years ago is just effectively just do what chemists do, right? Just grab a basis set from some database and try to use it. And the first thing that you realize is that these basis sets are really not optimized for solids, or not built for solids in any way. You find two very clear problems right away. If you take atomically optimized basis sets, they're going to have very small exponents that effectively kill you in a periodic environment. You simply cannot run the calculations at all. And this would happen with anything, all the alkalis and anything on the left-hand side of the periodic table. The other problem is that if you take even optimized, DFT optimized ones, which are the only ones that existed back then in a solid environment, they really have no idea what correlation is. They are optimized for DFT, and when you try to use them, they have no well-defined pattern that allows you to do any type of extrapolation. We built, for example, this is just a simple calculation for diamond. We grab the GTH, which are well-defined basis sets for periodic calculations of the CP2K package, and you see that what you get as a function of the cardinal number is nothing that you can rely on. If you build honest to God correlation consistent ones, you actually get nice and smooth behavior, but these things don't exist within solids. But I should say they don't exist until recently, because Tim actually put a paper recently where he actually constructed correlation consistent periodic Gaussian type orbitals. And so we are getting there in terms of having this type of technology, but I believe much more work is needed. The idea of having to find alternate basis sets in solids is not new, of course. The idea of using natural orbitals from MP2 or from RPA is something that has been pushed by the VASP group for several years now. And the idea of using mixed plane wave and periodic, so GTO means Gaussian type orbitals. I'm going to keep using this acronym around. So the idea of using plane wave GTO mixed basis is also being proposed recently. What we decided to do and we decided to explore is what happens, because it's what happens when you want to take this one step further. What we're proposing and what we end up realizing that works very well is the idea of mixing effectively Conchamp states with periodic Gaussians, but also optimizing the periodic Gaussians to the particular problem at hand, or at least to the particular element. Optimizing the orbitals within the solid environment, which would give you a very different expansion than what you would get if you do this within a molecular or an atomic environment. These days, we also add, even though this is not on the original paper, this is something we're doing these days, where you also add a few plane waves in your basis set to effectively take care of any long-range components. If you think about energetics, typically this doesn't help much, but if you want to look at momentum distributions or anything where you want to look at the low K behavior, this actually is relevant, as it would probably have a struggle from these two sides. In concrete terms, what we do and what we propose is we want to ease the transferability or make this basis construction a little bit more transferable. So we do take all the occupied states from a Conchamp calculation, and this is in a plane wave basis directly. That means that your reference energies and your reference Hamiltonian it's going to be done almost exactly. We typically, if you're doing something with the metal or something that has low lying states, we keep a few extra states from Conchamp. This effectively becomes some knob that you get to control. And we then add Gaussians to deal with the virtual states. We optimize these Gaussians by minimizing the energy, the MP2 energy, or it could also be the RPA energy, within some unit cell, some small unit cell of the system. And what we can show is that even though you're minimizing the energy on some small unit cell of the system, you can still use these spaces as you grow the system size, and the sort of the optimal or the beneficial convergence that you see remains. So something that is not very popular in for example, in chemistry, but in my opinion, is something that we should really think about in solids, given how expensive correlated calculations are in solids. If you're willing to spend the cost of doing, let's say, auxiliary field or couple cluster, which takes many orders of magnitude more than the construction of the basis, we can definitely, the construction of the basis either on the fly or for the particular problem is something that we can definitely pay, as long as the software and the workflows and the effort is sort of taken care of. This is just to show you what you get if you do this. And this is a simple example using lithium hydride in the B1 structure. In this case, I'm using a small unit cell just to look at the basis set convergence, not really thinking about size effects yet. The simplest thing that you can think of is just why don't I just take PBE orbitals or Conchamp orbitals, and I'm really behind. Okay. And so the answer is because they don't converge. They converge extremely slowly. And so if you think about the system size here, and that the penalty that you're going to pay on your correlated calculation being something like n to the 4th, n to the 5th, then reducing or minimizing the number of orbitals, the basis functions that you need to reach some level of accuracy, really pays off at the end. What we can say is that optimizing this mixed basis or using directly the natural orbitals from MP2 seem to be very efficient in both cases. You get very good convergence away. And with the idea of adding corrections to the correlated calculation, either coming from MP2 or from RPA, it also works extremely well. So if you see this is now using the optimal basis, you still have quite a significant amount of correlation it still takes quite a large number of basis functions to reach convergence. Especially in this case, this is MGO, sorry, I forgot to put the label, where the energy scale is now much larger. Even a triple zeta basis is still something like 100 millihartry away. But if you're willing to pay the price and calculate the MP2 correlation energy and use it as a correction post-processing, you're going to get something that's now on a very small energy scale. Similarly, and this is following recent work by Andreas Druneis and company, where they analyze the couple cluster expansion and the size, the basis set convergence of the different terms, and come out with a correction for couple cluster. Effectively, I propose this idea of the scale MP2 correction, which is identical to what he's proposing. If you take the correction to be sort of 1 plus the ratio of this PPL to the driver term. In our case, we don't have a way of calculating the magnitude of this alpha from a perturbative analysis, but if you take a 2-point approximation, you can always fit this alpha to any 2 points. What I'm showing here is what you get if you take the triple and the quadruple zeta calculations and you feed this correction. You can see how now you're getting within chemical accuracy, even for the triple zeta basis, where the basis set error on this scale is something hundreds of millihartry, whereas in this case, we're talking a handful of millihartry, essentially for free, because the cost of doing MP2 compared to QMC is much higher. And I don't have a lot of time, so I'm going to have to go a bit quick here, but effectively the idea is the same. We looked at these 3 materials, and the convergence is much faster with optimized basis. If we do bare MP2 corrections, the scale is actually much smaller. It's orders of magnitude smaller than the bare errors, even with the optimized basis. And if you're willing to go to this sort of scaled MP2 correction, which works much better, because in general, effectively what this is telling you is that MP2 is over-correlating. In all these scenarios, you get convergence that is much better. At this stage there, and I'm sorry, this is a busy slide and I don't have a lot of time, but if you're willing to go to that paper and take a look carefully, even though the MP2 natural orbitals look like, even better or very similar to the optimized Gaussians on single point energies, when you start looking at cold curves, and what I'm showing here is now the error that you're making as a function of the lattice constant for the 3 different materials and the different bases, sorry. This is MGO of the 3 different bases. You see that taking PBE orbitals leads to enormous errors when you look, for example, at things like cold curves, and even a base using 300 basis functions per atom is still giving you an error that is very large. The error bar on the lattice constant here would be enormous. And if we use optimized GTOs, the errors are pretty consistent across the lattice, the whole range of lattice constants. These are all optimized at a single point. They're not optimized for every calculation. So we optimize at the equilibrium distance and just reuse the basis everywhere. And you see that the transferability is pretty reasonable. The natural orbitals give you good convergence at each point, but that convergence is not systematic at different points. So you don't get a smoothly convergent basis as a result. So when you want to think about forces or bulk properties, you will struggle somewhat. I will skip this slide because I'm sure that I'm running out of time. But effectively, what this shows is that we're able now to get very well converged bulk properties at costs that are, on the double zeta, triple zeta basis. So we're talking somewhere between 20 to 30 basis functions per atom, and they're giving you pretty well converged quantities. And which is what we were looking for in the beginning. How much time do I have? 0. Okay, so I'm gonna say we have been looking now at spectra. If you want the details, you can go at this paper. This was work done by John Ho. He basically did a tour de force here in implementing the extended Koopman's theorem, and we implemented it in GPUs, and it's very highly optimized. And we can think about now the calculation of real-time spectra with auxiliary field using extended Koopmans. And the results are quite promising. For example, I don't have time, of course, but this is, for example, calculations directly in Diamond on a small basis set. And you can see that the results are basically, very, very close to things like EOM-IP, and even the exact answer within HCI, which is this heat path configuration interaction. So even though this is still in the preliminary steps, we have a path towards the calculation of real space spectra with auxiliary field, which we hope we can turn into something useful, combined with ideas of embedding and things like that in the near future. And I don't have time for conclusions other than to say that we're very excited about auxiliary field. We have a very ambitious agenda. All of this is going to be accompanied with code releases. Everything that we have been talking about here would be sort of easy to do with the one push of a button. And hopefully that code will be released soon. And thank you for your attention.
Thank you so much, Miguel. We do have time for one or two questions.
Miguel, when testing, say, for the adequacy of a basis set, when you're changing the lattice constant, if you try to fit bulk modulus and the Murnaghan equation of state, you would see kind of, first of all, you can fit the equation. Second, you can see the scatter of the individual points for a given basis set, and that gives you very easy visual representation. Is the basis set consistent to take, say, energy differences between the various lattice constants? Is there a scatter, whatever?
So that's how I got those numbers. You take the data, you fit it. The problem is that the basis set convergence is not uniform.
That's what I'm saying, yeah.
Right, so it converges faster, let's say, in some cases in the denser side than in the more dilute side. You need to be adding more and more functions until the curve itself converges. So what we're trying to do is to get to that converge point as quickly as possible without having to rely on brute force extrapolation.
Yeah, but it's not only the fitting that you'll get on the average perhaps well, it is the scatter from the curve. Do all the points sit on the curve, or do they kind of deviate, and how much? That gives you very quickly.
So in this case, it's auxiliary field, so there will be statistical scatter because we have error bars. If we were to do this with, let's say, MP2 directly, then it's a perfectly smooth curve. It's just that the shape of the curve is going to be basis set dependent, and you only get convergence at very large bases. But it's usually not something that scatters too much.
Okay. Thank you.
I should say when the basis is big enough. If you take something really small, then who knows? Yeah.
Maybe one more question.
So I must ask a little bit about the parallelization in the GPU. So GPU basically can be viewed as a multi-process, like you can run a lot of threads. So is that in your case, each thread will run a worker of the AFQMC, or is that something different?
So the implementation, we can talk offline as much as we want. It does take a completely rewriting of the code and of your mind. This idea of serializing calculations just doesn't work on a GPU. You have to rewrite the algorithm in such a way that you compact as much computation as you can in a concurrent manner, a parallel manner. So for example, we're processing hundreds of walkers simultaneously on each GPU. That's the only way that you get performance. Yeah.
And we'll do one Zoom question.
So sorry, there is a question in the chat saying, can you use a plane wave basis in auxiliary field? Yes, the answer is yes. This is a very clear competitive in terms of design. We push the local basis approach, but eventually the code that we release will also have a plane wave basis representation. The main issue that I have with plane wave basis is that you really need to combine it with a pseudopotential framework that lowers the cutoff of your plane wave. If you do this with, let's say, norm conserving and your cutoff is something like 100 Rydberg, which is somewhat standard number, the cost would be enormous. So the idea of plane wave AFQMC really is only compatible with a formulation that lowers the plane wave cutoff as much as possible. So we're working towards that, and things like combining it with PAW. And I should also say that Shiwei Shang, who's the pioneer of AFQMC in materials and in real anything, he has implementations in the plane wave basis, and they work really well. Yeah. And then there's another question: can one localize AFQMC when the system is insulating? There are ideas about that. Usually the code that we write, for example, can take a full advantage of localization. Is usually that the slowdown that you get on the numerics is not sufficiently compensated by the amount of locality. So you have to go to really enormous systems, have enough locality to compensate for the fact that sparse linear algebra is a lot less efficient than dense. So hopefully that answers the question. So yes, you can use it. It usually doesn't pay out. And how would you localize? In principle, anything that gives you a compact or a sparse 2-electron integral tensor would work. There are a bunch of ideas, any of them work, but you really need to get extreme sparsity, sort of on the order of few percentages. And anything above that, then the extra cost of the sparsity algebra doesn't make it pay off. Sorry, I was reading from there.
Thank you so much. Let's thank Miguel and all the speakers from this morning. We'll now take a break. We'll be back in about 25 minutes at 11:15. Thanks, everybody. Hello, everybody. Come on back in so we can get started for the second set of talks in the morning today. Should I go yell at them? I'll go clap in a second. Our speaker to begin this second session in the morning is Susie Latola from Mulsey at Virginia Tech. Susie, take it away.
All right. Thank you, Tim. It's my pleasure to be here, and I would like to thank the organizers for inviting me. This is my first time at this meeting, and actually one of my first times in a solid state standard electronic structure meeting. So I come from the quantum chemistry side, but I've been working on density functionals or implementing density functionals for a while. So this is the layout of my talk. I'll give a brief introduction, then talk about reproducibility, so issues with reproducibility. Then I have some solutions, and at the end is a summary. Okay, so as everyone here knows, DFT is really widely used. There are some 40,000 papers published on DFT every year. And the reason why it is so popular is that you avoid the exponential scaling correlation problem of wave function methods, and you only have to deal with the electron density, which is, of course, a much simpler quantity. The problem is we don't know the exact functional, and that's why we have to use density functional approximations. So, for instance, here is the functional form for meta-GGAs. They depend on the electron density at point R, the reduced gradient gamma at point R. Then you can depend on the density Laplacian or the kinetic energy density, or both at point R. So this FXC, this is the energy density at point R, and you can also write it in terms of the electron density times the energy density per particle. So this is often used in the literature. Okay, so if you look at traditional programs, the problem is they only implement a couple of functionals. So typically you might find that a given program has, say, like 5 or 10 functionals. So often it's the most common one. So let's say you have the Purdue-1 LDA, then you have the PBE functional, and often that's it. So depending on the field, so chemists use B3-LIP, at least traditionally, quite a lot. So you might have B3-LIP in a chemistry program and PBE in a physics program, and this, of course, leads to some issues with reproducibility. Like historically, you could not really reproduce calculations. You know, if the functional is not in your code, you can't reproduce other people's calculations. So reproducibility is an issue. And now the next question is, if I run a functional, is it the same? So it is not. So this is a 2021 JCP paper where they used ORCA, which is a Gaussian basis code, and MRChem, which is a multi-resolution code. You can do all electron calculations, get total energies, converge to microhartree or sub-microhartree accuracy, and then you can realize that, oh, like it actually makes a difference which implementation you use. And if you are interested in quote-unquote pissing contests, so marking basis sets to this kind of a precision, this is obviously an issue. Like you have to really have the same type of implementation in order to yield comparable data. Okay, so let's talk about some literature functionals. So my first example here is Purdue 86 correlation. So this is part of the BP86 functional on the previous slide. you look at this paper, and then you have this functional form where Purdue writes f is 1.745 times lowercase f. However, you look at the previous literature, and then you find out that, oh, 1.745, that's actually a truncated value for 9 pi to the power of 1/6. So if you have an implementation of the Landgraf-Mehl functional, there this value is used exactly. So you have a much more precise value for this constant, and then different programs implement this in different ways. So if you had implementation of the Landgraf-Mehl functional, you already have the precise value, and then the code started using that. So they just adopted the code, whereas fresh implementations, they might look at the paper and say, oh, like this is the number, I'm going to use this. Okay, this is all fine until you want to do precise comparisons. So this is a calculation on neon atom. So the Karlsruhe DEF2 SVP basis set. So this is a small split valence polarization basis set, and I'm just going to use a very large quadrature grid to convert the energy to very, very high precision. And indeed, you find out. So I used these 4 different codes, and there is a 4 microhartree discrepancy in the energy, and this arises from this constant. So different codes use different values, and the energies are not comparable. Next example. So Purdue 192 LDA relation. You look at the paper, it depends on the second derivative evaluated at spin polarization 0. So zeta is spin polarization. It's -1 for completely anti-ferromagnetic. It's +1 for completely ferromagnetic, and then it's 0 when you have a spin unpolarized density. Okay, so the equation for this f, which is a spin interpolation function, is given in the paper. It's pretty trivial math to evaluate what is the second derivative of this function, and you see that it has a pretty clear analytical value. So it's 4 divided by 9 times cube root of 2 minus 1. And you can evaluate this to many decimals. However, and the paper gives a truncated value for this. So it's not even approximate, it's equals. And now the question is, okay, what is the value I'm supposed to use? So if I read the paper at face value, of course, I should use the value they give instead of the value I calculate. Again, if you're not doing anything like too fancy, you don't care about microhartree difference. But if you want to compare different numerical representations, if I want to show that, yes, I can actually converge 2 codes for the same system to the same energy, this will prevent you from doing that. Next example, PBE exchange. So as you see, this is a very simple functional form. Exchange functionals, they're usually written in terms of this enhancement factor. So you have the LDA exchange density. So LDA, the expression for the exchange functional, that's analytic. So you can derive it from the homogeneous electron gas. And then you multiply it with this enhancement factor that depends on the reduced gradient. It can depend on kinetic energy density and so on for meta GGAs. However, so the PBE expression is quite simple. So around this calculation, PBE with exchange with the LIP correlation functional. So LIP is actually same in many codes. Around this calculation, I get 18 microhartree difference. And with the help of Gaussian developer, we're able to track down this difference into the original information of PBE in Gaussian. So they had slightly reorganized the functional form, and then they had truncated the parameter values. So this gives you a different energy, but like you can backpropagate these truncated values into this functional form, and then you see that your kappa, which is 0.840, that's known value. So you actually have to add some more decimals to this value, and the same thing for mu, which has a value given in the PBE paper, or this is actually from the reference implementation. So you change these, and then you're able to reproduce the energy from Gaussian to something like nanohartree, which is good. Okay, so I'm talking about kappa and mu here. Next slide. If you look at the PBE paper, they give an approximate value for beta. So you have 6 decimals. And then I note that actually mu is beta times pi squared over 3. And then they gave an approximate value for that. You compare these two values, you see that there's a difference in the last decimal. So if you use the approximate values from the paper, you can have like 2 different definitions. And then the actual reference implementation by Kieran Burke, who he actually distributed to, as far as I heard, to everyone on his email list or in his email. So the reference implementation was widely available. And that's why many codes, they do agree on PBE exchange. So the difference here, you see Gaussian is different. They probably didn't have Burke's reference implementation. Right, but then there's still this issue that when someone new implements the functional, so for instance, the XCFun library of density functionals, they do something non-standard. So they take the approximate value for beta, and then they compute mu from that. And then again, you end up with microhartree differences compared to the reference value. And a point I want to make about XCFun here is that they control functional forms by compile time declarations. So you can compile XCFun, and you can get different energies from different compilations because they're not implemented as different variants. They're implemented as the same functional, but the result depends on how you compile it. So if you define a macro, then the constant change, and then the energy changes. This is sort of not good. There's also many more examples. So these functionals by Peverati and Truhlar, there's actually typos in the paper. So the arrays are given the wrong way. So if you implement the functional as given in the paper, it's of course you get complete garbage because these are not the right parameter values. All right, I think this was the last on parameters. So now about functional forms. B3-lib, the infamous functional. You look at this paper from 1994 by Stevens and coworkers. They implemented this functional in Gaussian. So they actually used the form originally proposed by Becky, but they didn't have the same functionals in Gaussian that Becky used. So they replaced some of the functionals. They implemented the Voska, Wilk, Nusser, so VVN functional in Gaussian, and this is the form they give in the paper. But the problem is the VVN functional they implemented is not the recommended version. So the VVN functional, this was described in a 1980 paper. The paper is actually not very easy to read, and they describe several different functionals. However, there is a clear recommendation in the paper that this is the form we recommend, like this is the simplest form, but that's not the one they implemented in Gaussian. So they implemented a version that uses coefficients fit to random phase approximation data not the quantum Monte Carlo data of Sepperli and Alder. So this is a problem that they used or they described an incorrect functional form. It's not the VVN functional that had been established in the literature for 14 years. It's something different. So this had the unfortunate consequence of mixing up the literature terminology. So after that, people, at least in the chemistry community, they associated VVN with the Gaussian implementation, which is not the VVN that VVN described. So other code developers, they read this paper. Okay, they use the VVN functional. I use the VVN functional. And then you have discussions on the computational chemistry list. Hey, like I run this calculation in these codes, I get different results. Why is this? And so there was a paper by Hertwig and Koch in 1997 where they explained that, yes, this is because they use a different version of the VVN functional. And nowadays, I think B3lib is the same in all codes. However, many codes do implement several variants. So the version re-implemented by others is sometimes called B3lib 5 because VVN 5 is the original VVN functional. And this is the problem with redefined terms. So VVN turned out to be, is nowadays called VVN 5 for clarity. So yeah, it's really unfortunate. So who here has used the HSC functional? So this is a funny story. There's two HSC functionals, HSC 03 and HSC 06. HSC 06 is the functional described in this erratum. So they noticed that actually the 2003 implementation, the code used different values for the range separation parameter in the density functional part and the exact exchange part. So instead of using the same value, it used two different values. And then the HSC 06 functional is the same functional, but now you use the same parameter for both pieces. And yeah, so this is interesting when you have, you have a paper that describes the functional form, and then you have the reference implementation that describes, that's something else. Like, which are you supposed to trust? So I tend to go with the code because that's how you reproduce the results. And then if there is an erratum, then that's a new functional. And yeah, here's a few examples for recent functionals where the implementation is actually not what they describe in the paper. So this is like what we implemented in libxc, and this is how we reproduce the numbers from the reference implementation. And this last one is still in progress. We're communicating with the original authors and figuring out why, like, which one should we put in. Okay. So I've described that there are issues reproducing density functionals, and now I'm going to describe you solutions. However, we first have to discuss some issues in implementing density functionals. So how do we know that the implementation is correct? An issue here is that if you have a meta-GGA, you have 9 input parameters. So you have the density, that's spin up and spin down, 2 variables. Reduced gradients give you 3 more. The Laplacians and the kinetic energy density, that's 4 more. So you have 9 parameters. Now, when you are doing a DFT calculation in a code, you actually need higher order derivatives of the density functional. So if you do a self-consistent field calculation on the Gaussian basis, you typically use the trick of partial or integration by parts. You only need the first derivative. If you are doing following the solid state, basically conventions, so there you construct this effective local potential. You need to take the divergence of this like gradient term. So you need second order derivatives. And then if you want to do analytical Hessians of TD-DFT calculations, you need fourth order derivatives. And the problem is, by the time you get to fourth order, you actually have something like 500, or actually you have to sum these. So you have order 1000 equations that you need to implement. And obviously, you're not going to do this by hand. You need an automated approach. And the second issue is that there are many DFAs in the literature. So a talk by Miguel from 2012, there he estimated that probably, of the order of 250 to 300 functionals have been published, and now we have over 600 in libxc. So there is a giant zoo of density functionals, and they still keep on coming out. So this is an excerpt of the functionals that we have put into libxc recently. You have a variety of density functionals. So the obvious solution here is to have a standard modular implementation. So you don't have to implement the functional separately in every single code. You can just use the same implementation no matter what your code is doing, because the functional is always the same. PBE is PBE, B3lib is B3lib. So this function exe is always the same. The only difference is what derivatives you need, and libxc has all of them. And this just makes it much simpler to reproduce calculations. Use the same functional implementation, your results are automatically comparable. You don't get these micro-Hartree level differences in energy. And added bonuses are your code is easier to maintain. You can reproduce calculations from the literature. So, I wrote a code 10 years ago. I just update the version of libxc and I can run the new functionals in it. I don't need to modify anything. Like if you have MetaGGS implemented, you can run new MetaGGS with the code. You can also run very old functionals. So this is the beauty of modular software development. Bugs can be fixed in one place, and then they become the fixed version is available in all the codes that use this library. So yeah, this is the latest reference to libxc. So it's a paper we published in 2018. I worked on libxc since something like 2014, when I had been using it in my own code, and I found out some problems with it. And instead of fixing the issues for myself, reinventing the wheel, I started contributing patches upstream. And yeah, so in 2014, I became a developer, and I'm now I guess the lead developer of libxc. Okay, so a few words about libxc. So again, it's a library that implements a huge number of these density functional approximations. It also gives you stuff that is not included in the density functional approximation itself. So for instance, B3lib is a hybrid functional. It has, I think it's something like 20% of exact exchange, so Hartree-Fock. So libxc gives you the fraction of Hartree-Fock you need to add in to the functional to get the whole functional. So you can't evaluate exact exchange based on the density only. You need more information, which actually also depends on the numerical approach you're using. And yes, so you can use this regardless of the approach you use. So plane waves, Gaussian, finite elements, real place approaches, whatnot. And you get automatically comparable calculations. So we have exchange correlation, and kinetic energy functionals, pure functionals, global hybrids, same range separated hybrids. We have up to 4 derivatives. Of course, the functionals might not actually be differentiable, but libxc will give you the derivatives. So R2scan, for instance, is a piecewise definition. So higher order derivatives are not going to be very good. Importantly, we are licensed under the Mozilla public license. You can use libxc in commercial codes. So now we are close to 40 programs. This is an old slide, so I haven't updated this, but as you see that there are many different approaches. So Gaussian basis codes have recently become our biggest user. So it's now struck through in the quantum chemistry community. People are very happy that we provide them with stable implementations of new functionals like R2scan. We are now using just Maple to implement functionals because this just makes things so much simpler. So we actually can do these forced derivatives. You only need to implement the energy density and the code will automatically generate analytical derivatives. So yeah, I already mentioned R2scan. So the problem is that if you look at the R2scan paper, it's something like 4 pages of equations. However, building on top of the previous functionals, so scan, rscan, and PW92, the implementation in libxc is something like 100 lines of Maple code. And we implemented the functional within 1 month of the publication of the functional. So here's an example of PB exchange. So I've highlighted the functional in red. This is what libxc evaluates. And as you see, it is exactly the equation just in Maple format. So this is the enhancement functional. And then we convert the x, which is the reduced gradient without this like prefactor. So it's the norm of the gradient divided by the density to the 4/3. And then this routine takes care of all the components. So you get spin up exchange and spin down exchange. And the parameters are defined externally. So how do we make sure our density functionals are correct? There is the issue of these parameters, which are sometimes incorrect or ambiguous, or the original implementations are incorrect. So what you need to do is you need reference energies and the reference source code. This is a big issue for me personally, because it's basically every time I have to hunt down the original developer and ask them, hey, please give me converged reference energies. Please give me your source code because I want to be able to match your implementation to MicroHartree. So I want to plug my recent paper here. So unavailability of programs is no longer an issue. You have free and open source programs that can run these calculations. You can use your laptops. Student can run realistic calculations. And here's some examples. Like you can just brute force. You use the same, like bigger and bigger quadrature grids. You can converge the functionals to very high precision. So scan is famously unstable. You can't converge it to MicroHartree, even with huge radial grids. So there's going to be a paper published soon with these Hartree-Fock densities. All right, I'm out of time, so I'm just going to wrap up. As I said, there are ambiguities in functionals. There are different implementations. However, you can get functionals to agree if they use the same form. And the problem is people have not published accurate reference energies and the source codes. So if you ever review a paper on DFT functionals, be sure to demand these. You should not be able to publish a functional without publishing the source code. For calculations, just use libxc. So this recent paper on the archive, libxc also gives you the literature references for the density functionals. So cite libxc with the density functional and mention which version of libxc was used. And I would like to thank the NSF for funding for the MOSI, which is where I have been working on libxc for something like half a year recently. Miguel Marquez is the original author, my collaborator, and then Gas Kuseria, Victor Scritarverov, and Giovanni Scalmani helped me debug these discrepancies in the Gaussian total energies. Thank you.
Fantastic. Thank you, Susie. Never in my life have I been more self-conscious about writing papers. We have a question in the back.
Susie, thank you very much. I guess a couple of questions. A quick one is, what's the status of libxc on GPUs? And the second one is as you mentioned briefly for the scan potential, but for others, there's sort of like, you get close to numerical instabilities in a lot of these special function forms. And so there's a lot of hidden parameters often to navigate around that. I mean, sort of fudge factors in code. So what's your experience with that?
So the first question was on GPUs. Yeah, so we do have GPU support. We are actually in dire need of people to test. We've recently improved the GPU implementations a fair bit. However, neither me or Miguel are CUDA experts. So we would really appreciate some input on that. And the second question on these fudge factors and so on, it's actually very good. There are lots of functionals that have a lot of like truncations in them, like the HSC functional. They do lots of scalings. This shows up as numerical instabilities. And yeah, that's issue to be basically discussed. So we have a manuscript on this. We're hoping to get it out in the next month or so. However, so there are many functionals that are rock solid. So you converge to machine precision energy with something like 100 quadrature points, whereas these recent meta GGAs like MVS or especially scan, you need hundreds.
Thank you for the presentation. Is there any consistent effort to implement different functionals in atomistic codes for generation of pseudopotentials that are consistent with the solid state exchange correlation? So the whole result of the tests can be consistent from the atomic point.
Yes. So obviously, when you do something like a solid state calculation with pseudopotentials, then you should use the same functional in your atomic code to generate the pseudopotential, and then in the actual solid state code like plane wave. And this is basically where libxc originated. So it originated in Octopus, and then there have been a number of these DFT libraries. So I think the first ones were proposed something like 20 years ago, but then a lot of them just like died down pretty quickly. They never became widely adopted, unlike libxc.
We'll just do a quick check of Zoom to see if there are any other questions before we wrap up.
Okay, so there's a question on Zoom about a standard DFTD library. This is an issue we have thought about in libxc. However, in talks with the community, we realized that maybe it's better not to do this because the Grimme Group who developed the DFT-D approaches, they already have standard implementations of DFT-D. So they have the DFT-D, DFT-D3, and DFT-D4 libraries that accomplish exactly this. I'm not sure whether they implement the parameterizations of other workers in the field. However, they do have the most common ones as far as I know.
Okay, great. Let's thank Susie both for a great contribution to our community and for a really nice talk.
Hello.
So our next speaker is Kai-Sin Liu from UT Austin, who will tell us about real space methods for large-scale electronic structure calculations. Please.
Thank you. First, I want to thank the organizer for the invitation. And I'm really happy today have this chance to share with you our recent work on real space method for large electronic structure calculations. And I'm Kai-Sin Liu from the Trade Calculus group at UT Austin. And first, in this talk, I will give you some motivation why we want to do large scale calculations. But from the previous talks, I guess we already given a lot of enough motivation on this. And then I will move on to the method we use, the real space pseudopotential density function theory. And that's one efficient algorithm to solve the Kong-Shuang equation, which is a Chebyshev filter subspace iteration method, which I will give you more details when we come to later. And then I will introduce two projects we worked to improve upon the Chebyshev filter subspace iteration method. The first one is a specific curves based grid partitioning method. And the second is a spectrum sizing method. So first, why we want to do large scale calculations. And besides the motivations given by the previous talk presenters, here I want to give you some ideas. For example, on the left shows a silicon crystal, but for a very tiny one synthesized, it already contains 30,000 atoms. And on the right-hand side shows nanotubes, and it has tremendous applications in like catalysis or gas storage, etc. But to build a model for this, for a very short one, it also contains thousands of atoms. And besides this, if we want to study like a defect, like vacancy defect in silicon nanocrystals, or like the metric angles in recent 2D materials, all of these require a large unit cell. So all of these motivate us to develop a method to speed up the electronic structure calculations. So in the next few slides, I will start from density function theory and gradually include more and more ingredients and finally get the real space pseudopotential density function theory. So first, the density function theory tells us that the total energy is a functional of the charge density, and it contains an external potential felt by the electrons, and also an universal functional. And in Kong-Shuang's method, they approximate the universal functional using this the kinetic energy of the single particle orbitals, and also the Hartree and all the other many body effect that lumped into this exchange correlation term. And by taking the functional derivative of this, we will get the Kong-Shuang equations. And this is the main equation we want to solve. And from the solution, we can compute the charge density and get the total energy. And next, I want to talk about pseudopotentials. I think in most DFT calculation nowadays, we use pseudopotentials, but seldom to mention it. Yeah, so here I want to mention it is a little bit. So in the original Kong-Shuang equation, we need to solve the single particle orbitals of both core and valence electrons. However, if we can like incorporate the potential from the core electron into this potential and form this ionic pseudopotential term, then right now we only need to solve the single particle orbitals for the valence electrons. And another good thing is that the use of pseudopotential will set the length and energy scale to the valence electrons. So this will give us smooth and also knowledge wave functions of these valence electron wave functions in the core region. And this helps us to avoid some numerical difficulties when we try to solve the equation. And then for the real space formalism, here shows that if we want to solve a molecule here, then we will establish a real space grid around it. And inside this spherical simulation domain, we will solve the wave functions on each grid point. And beyond the simulation domain, we just assume the wave functions vanish. And this is usually a very good approximation. And here we can immediately notice one advantage of the real space method is that the convergence is controlled only by a single parameter, the grid spacing. And there are other advantages of a real space method, just like Claudia just mentioned, the real space QNC. She mentioned one advantage is that the real space method are easy for parallelization, which I will give you more evidence for that. And here I want to mention other points. The first is in real space method, we can avoid the use of faster Fourier transform. And this often prevents us from running even larger systems. So it's good to avoid this. And the second is in real space method, the resultant Hamiltonian matrix is usually very big. But fortunately, they are sparse. So usually we will need to implement our own matrix vector multiplication. And for that, there's a hope that we can make it fast and memory saving when we do that. And last, I want to mention that real space methods are good for nano-confined systems. For example, for the systems with DFAT or charged systems. Real space methods can also deal with periodic systems, but the methods are good at solving the nano-confined systems. And here I want to quote from one recent review paper on real space method by Frediani. And it says real space numerical methods are mathematically robust, accurate, and well suited for modern massive parallel computing resources. And I hope in the rest of my talk, I can give you some evidence to support these statements. So right now, combining the Kong-Xiao method and also the pseudopotentials and the real space formalism, we get the real space pseudopotential density functions theory. And again, this is our Kong-Xiao equation. And right now, and here is the Laplacian term for the kinetic energy. And here is the ionic pseudopotential term, Hartree, and extreme correlation functional. And all of these we represent them on the grid point. And here I want to mention again that in real space formalism, the Hamiltonian matrix is usually very large. It could be millions by millions, so it's not practical to store it. So instead, we will design a sparse metric vector multiplication subroutine to do the matrix vector multiplication. And usually in DFT calculations, we have to solve the Kong-Xiao equation repeatedly. And so this will be the bottleneck of DFT calculations. And usually in our experience, solving this will account for over 80% of the computation time. And fortunately, there's one efficient algorithm to solve the Kong-Xiao equation for the real space method, which is Chebyshev filtered subspace iteration method. And in this method, we focus on solving the invariant space of the lowest energy state. And in this method, there are 3 steps. The first, we will do a filtering to amplify the lowest energy state in the subspace. And then we will do optimization and ray reads to get eigen pairs from the subspace. In the next few slides, I want to go a little bit deeper into these steps. So first is the filtering, which is to enhance or amplify the lowest energy state. So initially, we will generate the subspace randomly, and because the randomness, the eigen component in the subspace will spread all over the spectrum. But what we're interested is often only the lowest energy state. So what we do is to apply a Chebyshev filter looks like this to the subspace. And you can notice that for the lowest energy eigen component, they will be amplified. But for the higher energy eigen component, they will be suppressed. And mathematically, we can look at this operation like this. We will form a Chebyshev polynomial of the Hamiltonian matrix, and we will apply this operator onto, let's say, one random vector. And in general, we can expand the vectors using the eigen components. However, we don't know the coefficients yet. And we just move the polynomial inside the summation and apply it on each eigen component. And this will give us the polynomial of the eigenenergies. So if the eigen component has an energy that falls in this lowest energy region, then the corresponding eigen component will be amplified because the factor is large at that region. So afterwards, for the new vectors, it will have a strong component of the lowest energy state. So we just do the same thing to all the wave functions in our subspace. So the subspace will have strong component of the lowest energy states. And after this, we do optimization to also normalize the subspace we just got. Here, I want to mention that we use Cholesky QR to do the normalization instead of Grand-Schulmin algorithm. And on the right-hand side, we can look at the orange bars, which is for the optimization steps. And you can see the Cholesky QR is almost an order faster compared to the Grand-Schulmin method. And this is because in Cholesky QR, we use most of them are matrix multiplications, which are more efficient. And after this, we just do the standard ray-reads method, which can help us to get the eigenstate from the subspace. So okay, so this the Chebyshev filter subspace iteration method is pretty simple, and we implement this in our code PARSEC, which stands for Slope Potential Algorithm for Real Space Electronic Structure Calculations. And you are very welcome to check our website for more details. Okay, so here I want to show some benchmark result of this algorithm. So here shows one the result for one tiny silicon nanocrystal, and you can see for the ChEFC, the Chebyshev filter substrate iteration method, compared to the other two methods, the CPU time is almost like 5 times or an order faster than the other two methods. And on the right-hand side shows the density of state of the biggest system we can solve by LAN, which is a silicon nanocrystal contain about 10,000 atoms with the assistance of symmetry. So this looks great, and it seems the ChEFC works pretty well, but there's always improvement that we can work on. So in the second part of my talk, I want to talk about 2 projects to improve the Chebyshev filter subspace iteration method. The first one is specific curves-based grid partition method. And the second is spectrum sizing method, which is used to overcome this one limitation in ChEFC. And this method can help us to overcome that limitation. Okay, so let's go a little bit back to the Kohn-Sham equation. So in the Chebyshev filter subspace iteration method, we will do a lot of the matrix vector multiplication. And in the matrix vector multiplication, there are two terms that are most costly, which is the Laplacian and the ionic superpotential operator. And they are both of them are non-local operator, which means when we operate then on a wave function, we not only need the wave functions from the current grid point, we also need the wave functions from other grid point. So you can imagine if we have good grid partitions, then there's a hope that we can reduce the communication overhead and also to make the computation faster. And the specific curves can help us achieve that. So in the next few slides, I want to give you a brief introduction to the specific curves and also some benefits we can get from using the partitions. Okay, so first, specific curves, they are one-dimensional representations of the multi-dimensional space. So for example, here we have 2D space planes. So these specific curves that will pass through the grid points on the 2D plane. And these specific curves, they have interesting properties. For example, they are self-similar, which means we can notice the bottom left panel here. Actually, we can get it from the previous generation. We just take the previous generation and rotate it and scale it and just pass into this region. Then we can get the grid point here. And for the other three panels, we just do the same thing. So the rules to generate these specific curves are usually simple. And you can imagine to generate the next generation, we just follow the same rules. And the second good properties they have is that they have good locality, which means for the grid points, which are physically close together, usually there's a high chance they will also be close in the specific curves. So for example, these first four grid points, they are physically close. And in the specific curve, they are also close. And in fact, in this case, they are continuous. And this can help us not only reduce the communication overhead, it can also help us to compute them faster. So let me give you show you some benefit that we can have from the use of the specific curves basic grid partitions. So the first one is that we can reduce the communication overhead. And here shows one illustration. So here we have 4 processes, and we want to update the wave function on this grid point. And we would need the wave functions from other from this ray dot. So in order to do this, process 2 need to talk to all the other processes in order to update this grid point. However, if we use grid partitions generated by using the Hilbert specific curves, then you can notice that right now, if we want to update this grid point, process 2 doesn't need to talk to process 4 anymore. And you can imagine that if we want to run large calculations, we will have like thousands of processes or more. So it will be a huge savings to apply these grid partitions. And the second is that specific curves can help us to enable the blockwise operations. And in computer science, people may call it a blocked version. So here shows that instead of updating one grid point at a time, actually we can update multiple grid points at a time. And in this case, we can update 4 grid points at a time. So this can also help us to speed up the calculation. So in the next few slides, I want to show you some benchmark result using these grid partitions. So the first is the speed up for the matrix vector multiplication subroutine. So here shows the speed up across different problem size. And we use the simple Cartesian ordering, the naive way to our baseline. And let's look at the blue bars first. which are the block-wise simple Cartesian ordering. So here we just include the block-wise operation. And you can see the speed up is about 2 across different problem size. And then we include more. The grid partitions generate by using the Hilbert specific curves. And in sum, they will give us a speed up about 6 across different problems. And also we can look at we can look at the communication volume that when we do the metric vector the blockwise Hilbert method, the data amount of it is about an order less compared to the simple Cartesian ordering. And on the right-hand side shows the strong scaling. And you can notice for the blockwise Hilbert method, it can sustain a very good parallel efficiency when we use 1,000 processes. But for the simple Cartesian ordering, it will drop to about 20% compared to the ideal case. So this enables the use of specific curves based grid partition method can help us to push the limit a little bit of the size of the calculation we want to do. So here shows one example for a silicon nail crystal with silicon 50,000. And here shows the density of state of the silicon nail crystal. And we can compare to the bulk silicon. And you can see they are almost indistinguishable. And one thing interesting us is that in this calculation, we don't use a Bloch theorem. However, we can clearly see the features, the Van Hoff singularities, as the same as in the periodic calculation. So this makes me wonder what's the physical meaning of the K in the Bloch theorem. And can we do even a larger system? And yes, and this result just came out 3 days ago. So here is one size bigger than the previous one, silicon 100,000. And the result is this preliminary result because we haven't converged yet. But you can already notice that the density of state is already very close to the bulk silicon. And also for the valence bandwidth and also the energy gap is also very close to the to bulk silicon one. So can we do even larger? And unfortunately, we don't have that yet, but probably for the future. So be able to do these size systems, we can look at examining the evolution of the density of states from tiny silicon nail crystals right up to its bulk limit. And we can see the formation of these Van Hoff singularities in these simulations. Yeah, so although this looks great by using the specific curves based grid partition method, however, we also notice one limitation for the Chebyshev filter substrate iteration method, which is the qubit scaling operations start to dominate the calculation. And on the left-hand side shows that the timings for the 3 steps, the filtering, optimization, and Rayleigh's procedure in each calculation. So you can see for the last 2, they will start to dominate the calculation as the signal size goes even larger. And this is because for the later 2 steps, their time complexity are proportional to the cube of the system size. So right now, what we try to do is to reduce the number of states effectively. And this is where the spectrum sizing method can come to help. So here shows that the spectrum we want to solve, and usually we need to solve all of the eigenpairs at the same time. However, if we if we use the slices like this, and each size, for example, size 1, use a spatial filter like this, then it can constrain the problem size within this region. So size 1 only need to solve the eigenpairs in this region. And also the same for size 2 and size 3. And the best thing of this is that they can do this in parallel. So this can effectively reduce the number of states each slice need to deal with. And compared to the original Chebyshev filter substrate iteration method, we can look at like this. So for the filtering step, we can all the processes can do the filtering in parallel. That's no problem. However, for the optimization and reads procedure, all the processes need to participate in these steps. And in spectrum sizing method, we put an additional layer on top of these 2 steps. So this can increase the scalability of the Chebyshev filter substrate iteration method. And to do a quick recap, so in the spectrum sizing method, we will divide the original problem into sub-problems. And we will use the Chebyshev filter substrate iteration method on each slice in parallel. And after every slice solve the eigenpairs, then we just combine the spectra and calculate new charge density. And we repeat this procedure just like we do in a regular self-consistent field approach. And the rationale behind this is to shift the burden of the qubit operations to the filtering step, because for the filtering step, the time complexity is just proportional to the square of the system size, because the K here, the degree of filter is a constant. Okay, so let me summarize my talk. So in this talk, we use a real space pseudopotential density function theory and the Chebyshev filter substrate iteration method to solve this electronic structure of a system over 50,000 atoms. And this is empowered by the use of specific curves based grid partition method, which can help us reduce communication overhead and enable us to use blockwise operations. And also we proposed one polynomial filtering spectrum sizing method, which can add an additional layer on top of the optimization and reread procedure. And it can hopefully it can increase the scalability. And we hope by combining the spectrum sizing method and the specific curve grid partition method, we can achieve solving even larger systems. For example, maybe 200,000 atoms or 300,000 atoms. Okay, so at the end, I want to thank NERSC and TAKE for providing us the computational resources. And also I want to thank DOE for funding this project. And most important, I want to thank of the people here, especially I want to thank Chao Yang, who is our collaborator on the spectrum sizing paper. And also I want to thank Leo Konek and Ariel Biller, who are our collaborators on the specific curve project. And of course, all the people here, they have contributed to the past cycle over the years. And without them, we cannot do this project. And again, you are very welcome to check our website for more details on this project and the code. Yeah, thank you.
Thank you so much for the nice talk. We have time for questions in the back.
Thanks for that nice talk. Have you faced any difficulties while following this method? If yes, what kind of difficulties you faced?
Oh, you mean after the spectrum sizing, what kind of difficulty will we face?
Yes.
Yeah, I think one is that the spectrum size method right now is still, it's not very sophisticated yet. So we need to tune the parameters in order to converge the result or make it faster. So how to get good parameters for each type of systems? Yeah, I think that will be our next step.
Are there other questions?
So I guess in the calculations, the scaling is like n to the cube, right?
Yes.
So what's the maximum n can be done in right now, just in the algorithm?
Yeah, I think the issue is similar to what Miguel just mentioned the memory. I think it would be the would limit the problem size.
Okay.
Yeah.
So roughly estimate like just
Roughly estimate. It depends on the system because for different system we will use different grid spacing. Yeah, but for the silicon nanocrystal size, I think to run, for example, 8,000 nodes, then I think there's a hope to achieve for probably 300,000 atoms. I think that's maximum, limited by the memory. Yeah.
So can you comment on the difference between this code and the Siesta, which is also a real space code?
Yeah. Sorry that I don't have much experience on Siesta, but I know the one difference is the basis. In Siesta, I remember they use numerical atomic orbitals. Yeah. So I'm not sure for that part. Probably they can be. There will be more savings on the memory for Siesta because they use that orbital. Yeah.
I see. Thank you.
Could I ask quickly, are there plans to implement non-local exchange for global hybrid DFT?
Sorry?
Do you have any plans to implement non-local exchange, like Hartree-Fock exchange, in order to do global hybrid DFT calculations?
Yeah, that's the next step.
Okay.
Yeah, I think we have one proposal. Yeah, for that. Yeah, that's a very good question. Yeah, there's people want to do like using like many previous talk shows use higher order exchange correlation functional. By the way, we also use libXD. Yeah, so thanks.
I think we have 2 questions on Zoom we could take.
Okay, so on the Zoom chat, it says, ask what is the fundamental difficulty with using real space DFT method in periodic systems? Okay, that's a really good question. Yeah, so here I mentioned that we can avoid the fast Fourier transform in the calculation, but that's for the confined systems. So for the periodic calculations using real space method, in some part of the calculations, we still need to do fast Fourier transform. So I guess to some extent, to some size of system, that could be an issue. And this one. So the other question is it possible to combine the real space approach with periodic boundary conditions? Oh yeah, so yes, we can also do periodic boundary condition systems.
Okay, great. Let's thank our speaker again. All the speakers from this morning. All right, thanks everyone. We'll take a lunch break with lunch downstairs like yesterday, and we will resume here at 2 p.m. for the afternoon session. Thank you.
Okay, let's get started with our afternoon session. So my name is Cyrus Dreyer from Stony Brook and Flatiron, and I'll be chairing the session. And our first talk is Chris Marianetti from Columbia University, who will be talking to us about the ground state of a multi-orbital MOT system. So 30 minutes for the talk and 5 for questions. Am I using this mic? Yes, I think that's.
Can everybody hear me? Yeah, okay. I talk loud on top of it, so there's that. So I'd like to thank the organizers for putting this great conference together. I'd like to certainly welcome everyone who's come from all corners of the globe. It's very exciting to have something semi-normal happening in life. So yeah, I'm talking about this new variational theory that we developed. This work was the PhD thesis of my former student, Zhenshen Cheng, who's here in the front row, who's now a postdoc with me, one of the positive developments of the pandemic. So my group over the last several decades has done a lot of work, just to give you some big picture of where this is coming from, on density functional theory, merging it with dynamical mean field theory to have a theory that can treat strongly correlated electron materials. And so DFT plus DMFT is a very powerful theory. The main limitation is its computational cost. If you want to precisely solve the Anderson impurity model associated with DMFT, you basically need to use quantum Monte Carlo, which is very powerful, but it comes with a great computational cost. And so we've been working on developing more efficient approaches that can, retain the accuracy of these more powerful approaches at a much tinier cost. And we've done that by focusing on the ground state properties. So I'm going to tell you about this systematic variational approach that we've developed. Systematic in that, unlike many variational approaches, ours is unbiased in the sense that we know how to systematically approach the exact solution. We have an integer that we get to crank on and go closer and closer to the exact solution at, of course, an increasing computational cost. So what I'm going to show you is that we've attained an unprecedented balance of efficiency and accuracy in the multi-orbital Anderson impurity model and the multi-orbital Hubbard model in infinite dimensions. We can do, I'm going to show you later, the 2-band Hubbard model, we can solve it in something like 1 second on 1 core on a laptop computer. And this, for the experts in the audience, using techniques like quantum Monte Carlo, this is, using you would need a major computing cluster. So we're many orders of magnitude faster for a similar precision. So what is this VDAT? I'm going to tell you about it in some detail, but there's a lot of details. So if you're interested, you can talk to Zhenshen after the talk and he'll walk you through every single detail. I'm basically talking about what's in these 2 papers. We have a PRL which highlights some of the results, and then a very long detailed PRB going through all the details. But what is VDAT? It consists of 2 ideas. Like any variational theory, you need an ansatz for the wave function or the many-body density matrix. And so we have some ansatz, and then we have a formalism that we've developed, which is tailored specifically to evaluating this ansatz. So what is the ansatz? It's what we call the sequential product density matrix, the SPD. And this is inspired by the Trotter-Suzuki decomposition. You'll recognize it when I show it to you in a moment. And the SPD, you could imagine, is controlled by an integer n. And when n goes to infinity, you're guaranteed to recover the exact solution. Okay. And so then we've developed what we call the discrete action theory, DAT. And this introduces the somewhat unusual concept of an integer time Green's function. And these quantities sort of naturally emerge in the formalism if you want to evaluate observables under this particular ansatz. So we'll show you a little bit about that. And so VDAT, what is it? It combines this ansatz, the SPD, with this discrete action theory. And then, of course, you need to minimize over the variational parameters. If you can't do that, then this would not be a useful theory, but we can do that. Okay. Yeah. So motivating the SPD, if you consider some Hamiltonian, which has some non-interacting part that you can solve and some interacting part V, we can then construct an ansatz as follows. We can take the exponential of some variational parameter times the non-interacting part, the exponential of some parameter times the interacting part, and then we can take a whole chain of these up to some integer n, and then we can hit this operator on some non-interacting wave function. And from the Travis-Suzuki decomposition, we know once we take enough of these pieces and going to infinity, we can recover the exact solution. So this is kind of an obvious idea if you sit and think for a little bit. And indeed, when we look back through the literature in the 1990s, somebody, didn't really pursue this, but said, hey, this would be acute variational wave function. It would, recover the exact solution, X, Y, and Z. So the idea, or at least the essence of the idea, has been out there for a while. And we, generalize this in some trivial way. But that is basically the motivation for our ansatz. So the sequential product density matrix then is simply the following. We have the exponential of some non-interacting operator where this dot is defined here. This is some non-interacting operator here. And then P is some interacting projector. And, again, we have n, mathcal n of these pieces. And the more and more of these pieces that you take, you're guaranteed to have a better and better solution. So with this SPD as a variational ansatz, you're going to monotonically approach the exact solution at some increasing cost. Okay, so we have an interacting version of this. We also have a non-interacting version of this density matrix, and that will be important to set up some perturbation theory to evaluate the interacting case. Okay, and again, to sort of show you the flexibility of the SPD kind of encompasses most of the variational wave functions that you know. Okay, so n equals 1 would recover, I guess I should also tell you some detail here. There's sort of two flavors that you can make this density matrix. You need to make it Hermitian and semi-definite. There's two ways to do that depending on which operator you put in the center. And we call these Gutzwiller type and Barry-Swell types. And so we're going to focus on Gutzwiller types in this talk. And at any rate, n equals 1 recovers Hartree-Fock. N equals 2 would recover the Gutzwiller wave function in the context of the Hubbard model, the Jastrow wave function, variational coupled cluster, unitary coupled cluster. N equals 3 recovers the Gutzwiller Barry-Swell wave function, a little bit more obscure for the experts in the audience. And then on the B type, you have some wave functions which you may not have heard of. And n equals infinity is going to recover the exact solution. So fortunately, the solution we'll show you converges very rapidly. Okay, so I've told you a little bit about the ansatz. Now I need to tell you about this formalism that we use to evaluate it, which is we call the discrete action theory. And the idea is that basically you're going to propagate your operators in integer time. And so the definition of, you have an interaction representation, a Schrodinger representation, a Heisenberg representation. So it's sort of like all of usual many-body physics is paralleled in this formalism. And what you can do is then, our goal, of course, is to evaluate all observables under this particular density matrix. And so if we write an expansion for some operator O under this density matrix, what you'll see is if you study this non-interacting non-interacting integer time Green's function, which by definition is this, that for finite systems or for infinite systems where local interactions are confined to some subspace, e.g. the Anderson impurity model, you can actually evaluate this with a finite number of diagrams. So you can literally write out the solution to this under those constraints. So let's jump to an example, because this is a lot of math at this point. So we're going to study the Anderson impurity model on a ring. This has been studied extensively with DMRG in the past few years. And we can compare the VDAT solution to it. Yeah, so this is the spin-spin correlation function which measures the double occupancy, some combination of the double occupancy and the density. And so we have the spin-spin correlation function here as a function of U over W. And you can see the DMRG are these dots. N equals 2, which recovers Gutzwiller, is here in green. Not bad, but not so good. When we go from 2 to 3, we go from green to blue, and you're already almost on top of the exact solution. And then from 3 to 4, you get even closer. So this converges very rapidly. This costs almost nothing to execute. So here's the total energy. And remember, the total energy, because this is a variational theory that we're exactly evaluating, you're guaranteed to rigorously produce an upper bound on the exact energy. So there's something very pure about these calculations. And you can see, again, Gutzwiller in green, N equals 2. And then we jump to 3 and to 4, and you're going closer and closer to the exact solution. This is the so-called unscreened spin. This is measuring correlation functions between the impurity and the math. Same story, Gutzwiller, not so good. As you go to 3 and to 4, you get closer and closer to the DMRG solution. Okay, so that's great. And that's the Anderson impurity model, but we want to study the Hubbard model. And doing the Hubbard model in finite dimensions, you'd still have an infinite number of terms to evaluate. But it turns out doing the Hubbard model in infinite dimensions, we can still exactly evaluate this ansatz. And so that's a big deal because it allows us to solve the Hubbard model without using dynamical mean field theory, without having to compute a Green's function. We can directly get to the ground state properties using a wave function and really study the Mott transition and all the related physics. So how do we do that? We have to sort of develop more advanced tools in this integer time framework. And we introduce